And so basically, I'll characterize modern manufacturing systems and talk about different types of systems, including digital and cloud manufacturing, and eventually we'll get to to universal manufacturing. Oh, that's funny. Okay, and basically we'll also emphasize some high-level modeling of manufacturing systems. So this is a summary of what I see in terms of developments in manufacturing. So if this is manufacturing universe, so in this manufacturing universe, we'll have open manufacturing that I'll talk about. Within open manufacturing, there is a manufacturing configuration that we call universal manufacturing, and these types of systems will make one extreme of manufacturing. The other extreme is made of integrated manufacturing. And so I'll define those various types of systems in the presentation. But before we go there, let's go back to year 2017. So in 2017, there was World Manufacturing Forum that took place in Monterrey, Mexico. And this is a slide that I'm borrowing from this conference. Basically, what you see here that usually most of us in science and in engineering, we like to focus on sort of disruptive progress. So we tend to assume that so there will be some kind of linear progression of developments in various domains, including manufacturing. But what could happen though? Before pandemic, it has been observed that sometimes maybe adverse events may prevail, such as environmental or pandemic. So the development is not going to progress as we have anticipated. Well, there could be also something severe happening with artificial intelligence that sort of prevails in many applications. And in the end, also even politics may impact developments in manufacturing. So this is very important, actually, graphics that we ought to remember, that focusing on just sort of narrow problem in this quadrant, it doesn't suffice. And that's really motivation for the concept that I call universal manufacturing, that we ought to also consider this environment around usual domain of our activities. So let's look at maybe some high-level definitions of different forms of manufacturing, from digital to smart, open to universal. So I have selected a set of attributes from flexible through agile, reconfigurable, resource sharing, data-driven, and including also serviceability as well as sort of globally optimized systems. So we don't have time to get into those definitions, but you can recognize that some of those go to 1980s to flexible manufacturing systems. So this term was basically at that time coined. Then we moved into sort of broader range of flexibility, including also cost and also broader functionality. We had agile systems. Then we talked about reconfigurability. So if I use these attributes, then these attributes can define really different stages of manufacturing systems. Well, obviously, digital manufacturing is driven by progress in sort of data availability, and there is obviously modeling. So that's the reason we talk about digital twin. Then we have smart manufacturing, which is covered by a larger subset of these attributes, so including reconfigurability as well as artificial intelligence. Eventually, we move to open manufacturing, which also is defined by a larger number of attributes, and universal essentially covers all attributes that I have defined here. So, as we move forward, we'll be basically talking about those different types of manufacturing. All that. Let's look a little bit at the history. So how the manufacturing configurations have developed over time. Many systems are actually, even present today, are essentially can be modeled with this graph, that you have one product, maybe with some variants of it, manufactured in one manufacturing system that we may call actually dedicated manufacturing system, because this system is essentially dedicated for this product. Even sort of automotive industry, so well, they have deviated obviously from this model. There's some changes structural changes have happened here, but still in early years and even to some degree today, they follow this model. So the natural progression from this dedicated manufacturing was to basically distributed manufacturing. So in distributed manufacturing, first of all, that we have geographical distribution, we have functional distribution here, and this distributed system accommodates many different products. So the relationship, rather than one-to-one, for the previous system, is many to one. So this is still this distributed system, but essentially this distributed system accommodates sort of many different products. If we move forward, then we'll end up with open manufacturing. So in open manufacturing, the relationship between products and manufacturing facilities or manufacturing systems is actually represented with this bipartite graph. Well, this graph doesn't have to be necessarily fully connected, because full connectivity here implies that any product can be manufactured at any of those systems. This doesn't have to be necessarily applied in actual practice, but I think that this model holds, that essentially this is many-to-many relationship. So you see that we are having sort of more flexibility, because product one can be actually manufactured in any of those three systems. Well, there could be different, maybe productivity, there could be different quality that will result from maybe some of those assignments. But I think that it's important that we have made the entire system more flexible. Now, so let's sort of summarize that open manufacturing makes this extreme of sort of emerging manufacturing envelope. Integrated manufacturing makes the left extreme. So as you see that this open manufacturing is highly flexible, while integrated manufacturing, well, it's specific. It also implies innovation, which of different kinds than the one that is going to take place in open manufacturing. So integrated manufacturing is a case where a company, or could be individual, develops a new material, new process, and new product. So if someone has developed three of those entities, then basically it's not likely that the knowledge about it will be shared. That we will basically take all details and post them right in the cyberspace, somewhere in the cloud. So while open manufacturing will have presence in the cloud, in the manufacturing cloud, integrated manufacturing is going to have presence, but actually in a different sense. Now, I think we hear some background, someone is doing something around, so disturbs a little bit. So in other words, that you see, so those are two extrema, and that's the reason I call it extreme manufacturing. And in between, there will be hybrid models or manufacturing as we see today. So over time, I think that what's going to happen that this integrated manufacturing is going to basically expand. Also, open manufacturing is going to expand. So the middle portion is going to shrink. So I think the future will show how fast we'll get to this concept. Now, at the core of this is actually manufacturing as a service or service models. It's sometimes difficult to imagine that manufacturing can become a service. And I'm talking about this manufacturing processes here. But actually this is happening. It doesn't mean that all factories will become service factories. But I think perhaps majority of them, at least many of them, will work in a service mode. So essentially, manufacturing will become a service. Well, this is example at the maybe one machine level. This palletizer is actually marketed as machine as a service. So this is so the company doesn't want to sell it as a product. It actually sells as a service. Now, you can look at larger scale facilities such as Foxconn, for example, and you'll see that they are essentially contract manufacturers. So what they do, they perform manufacturing service for product developers like maybe Apple. So Apple doesn't have to own any manufacturing facilities, and yet they may manufacture products because they are using service. And companies such as, well, maybe like this one that would own this palletizer, or Foxconn and similar companies essentially perform service for companies. And this service notion is going to expand. It's going to move into product development. Well, supply chain, we see this already. It's happening, supply chain and distribution, but we'll see. Logistics is probably also, this is by taking manufacturing enterprise logistics, because in some logistics areas, this has already happened. Even we go into such detailed function like maintenance that this also become service. So essentially, almost everything will become a service. So this is the assumption that we are making here for the future. And this, well, and how this is going to work, basically, let's look at what is the relationship between maybe product development and manufacturing today. So today we design and manufacturing is tightly integrated. But what are we doing when we are designing a product? So we know that a product cannot be designed in abstract of manufacturing. It has to be designed for manufacturability. By this, we imply that we design product for dedicated manufacturing. Because what we have in mind today is specific manufacturing processes. But we are moving away from it. And this is what's going to happen. So when we end up with universal manufacturing, we'll be actually designed for systems that we don't see, we don't own, they just exist. And once we complete design, then we'll have many manufacturing options, because those systems will exist in the cloud. And what we are going to do, we are going to select specific manufacturing processes, specific manufacturing solutions to basically manufacture the product that we have developed. In fact, it's conceivable, and it's going to happen, that a company or individual may basically design a product, and to design it, that person or that entity doesn't have to own any design facilities. This again, this could become service. So they could use design service as well as manufacturing service. So and to do this, we need modeling. Some of it could be accomplished with process models. So as you can imagine that now every manufacturing facility will gain presence in the cloud. Well, to be present in the cloud, you don't want to show your graphic. I mean, you need to show some models, because it's not enough to take a photo of your company or your machine and post in the cloud. This would not get us far. To make it working, we need to post models in the cloud. And one way is to actually use process models. So we don't have to start from scratch, because we have over 70 different process modeling methodologies. So we can use maybe languages such as systems modeling language, which is more or less, resembles sort of like language that we use for coding. Or we can use more graphics-oriented modeling methodologies, such as business process model and notation. Maybe this is not the most suitable methodology, but one of the reasons I picked it up, because it has an ISO standard. So in essence, this methodology serves as universal language. If I have universal language, then I can describe any manufacturing facility in this universal language, post in the cloud, and then basically processing will be, digital sort of processing, information processing will be feasible, because I'll be able to search this database for those models that will imply specific manufacturing capabilities. Now, so let's take a simple example to explain this concept. Assume that I'm a manufacturer of this bottle. This bottle has only 3 components. There's actual bottle here, container, cap, and a tube. So my manufacturing facility that I use today looks like this. I use a tube injection machine, this cap injection molding machine, and this container, this bottle injection molding. So I have produced 3 components injection molding, and I am actually now assembling this bottle, and that's my that's my final product. Now, assume that someone wants 3 times as many bottles to buy as 3 times, or maybe 3,000 times more bottles that I'm manufacturing right now. So imagine now, how would you increase production capacity according to today's capacity expansion model? Well, you would have to sort of look for investment, build up this production facility. There will be hesitation, because it would be difficult to convince a chief financial officer to sign off on this investment when perhaps the order is not just secure. There's maybe some uncertainty. So in today's model, we'll have, and we've seen this, that companies have difficulty to just scaling up rapidly. But this is going to happen in the future quite often. So in order to meet this perhaps very variable demand, we need to move to this model of universal manufacturing, where we have facilities represented in the cloud, and just a simple search will lead us to the selection of the various alternatives. And obviously, there's always capacity somewhere available that can be used to meet this demand. So this concept will change the nature of manufacturing as we see today, because you'll have large manufacturers and small manufacturers present in the cloud. So now the benefit to small manufacturer will be that, well, they'll have more opportunity to be selected. So the competition will be more fair. In essence, this will contribute to democratization. So this will convert the manufacturing, as we know, to really more democratic manufacturing. Because right now, larger manufacturers may take advantage of smaller manufacturers. Smaller manufacturers don't have resources, don't have ways of selling themselves. And this concept of universal manufacturing will allow them to be present and to basically engage in meaningful contractual. So how can this be done? Actually, this can be done in two ways. So what I need is that, well, those are the products that I'd like to manufacture in quantities that sort of are projected. So what I will need is standard interface, and this is something that we have to agree on, as maybe we have to agree on this universal language of communication. So BPMN methodology is an example. We also would have to agree on some kind of a standard interface that we could actually use to basically enable communication between products and manufacturing facilities that exist in the cloud. So this would be one way, sort of product way. I could also so as you see here, that eventually product can be, it includes some assemblies, components, and eventually those lead us to specific machines or manufacturing capabilities. Just basically services. Those are, in general, we'll have at the bottom level here various services that would be basically requested by this model. The second option is go directly through process specifications, through manufacturing specifications. So this approach will apply to established products. The first maybe approach is when someone develops a new product and basically goes through this cloud to find the most suitable manufacturing facilities. This is the approach where we go through manufacturing specification, because we may have existing product and that there was a need to produce in much larger quantities, or maybe there's some redesign that has taken place. So since we have information about manufacturing processes, so this is a quicker path to finding the basically configurations. So in essence, this is what's going to happen. So this was this bottle, this was my manufacturing system, and since demand has increased 3 times, that I went to the cloud, to the universal cloud, and I was able to find those 3 configurations out of just many that were present, and basically those I'll be using for manufacturing this product, maybe for a period only a month or short period of time. So this is opportunity that I was able to take advantage of because of this basically manufacturing. Now, if I wanted to formalize a little bit this process, how it just basically take it much closer to maybe modeling, to implementation, that basically this calls for having some kind of a table, some matrix that you'll have when you specify manufacturing capabilities. And this is just not only machines, but tools and sort of all type of services as well as software. So this will be a very large scale matrix. And those will be specific sort of manufacturing systems that will be present in the cloud. So what I need is basically a relationship between the manufacturing system that are owned by different companies and machine tools. In addition to, I need an additional piece of information here, which has to do with this similarity matrix. So this similarity matrix is between various machine tools and resources, because there will be, there could be identical machine tools, but there could be machine tools and other resources with similar capabilities. So this could be expressed in some sort of a similarity matrix. So it's, in summary, I need basically this matrix that shows relationship between machine tools, or in general manufacturing resources and manufacturing systems, and a second matrix where I have relationship between manufacturing resources, in particular machine tools. So those are two major pieces of information. Now, this algorithm, which I call it enterprise configuration algorithm, would do all the processing and select component models that would make my future enterprise. So this is not my final configuration of a system that will be able to manufacture to meet this 300% increase in demand. Those are just component systems. So in addition to basically this previous algorithm, I need to apply another one to synthesize those components models, because I may have many, because those models will be not just for machines as sort of illustrated in this example, but for all type of resources and services. So they may have hundreds of different models, and therefore we need algorithms. So another algorithm, I call it synthesis algorithm. So the previous was configuration, determine the basically component model. I'll have another model, I call it synthesis algorithm. And this synthesis algorithm will take the components model and assemble them into final enterprise models. So how this can be done? Well, if I just consider this example of those partial models that I have here. So they can be represented again in another matrix, sort of like a machine, this is resources, also in this case is machine matrix. I'll show relationship between those basically blocks here in this matrix. So in essence, those are precedence relationships that are sort of recorded here. Like between machine 5 and 3 is twice, because 5 and 3 is here, and also 5 and 3 is also here. So it's just happened twice. So this matrix here just represents basically this graphics. This is matrix representation of this basically graph, and the algorithm will do transformation of this matrix, and in essence, in the end, I'll just get this model. So those partial models will be synthesized into one model. So this is a just brief illustration how this can be sort of accomplished. Right? So as you see, basically, so first of all, what we are showing here that in order to move this with manufacturing forward, we do not have to reinvent everything. That we have some valid methodologies, including this engineering modeling methodologies. So model-based systems engineering in general, and that can be used to represent systems. The greatest benefit of this methodology is that some of those basically methodologies have become standards. So we could use this universal standards across the globe. Now manufacturing obviously is moving forward. So it's going to becoming more open on one end, then also integrated will be the other extreme. And this is important because we don't have time to talk about this, but those two different models will call also for different type of innovation models. In general, manufacturing will become also more democratic by being present in the cloud. Also resiliency, so the first quadrant can be easily addressed here, and the likely is becoming universal. So I guess this is all time I had for this presentation. I always usually I use a lot of I use references, so those are this course of universal manufacturing. It's going to appear in the International Journal of Production Research. In fact, there will be a special issue on the 60th anniversary of the journal. So this is one of those papers which will be included in the anniversary issues. Well, thank you. It was great talking to all of you, and I'm happy for answering any questions that you might have.
Thank you very much, Professor Kusiak, for the very interesting talk. So I would like to start
Yes.
asking audience if there is any question. Please feel free to raise your hand, and
or go to chat, maybe chat or something. Yeah, sometimes in chat also works, right?
Yeah, no problem. They can also switch on the microphone and the camera, and it would be very nice to start a conversation. So I see already two questions. The first one from Ashley Ramos.
Mm-hmm.
Feel free to make the question.
Sure, thank you. Thank you very much, Doctor. It was an amazing presentation. I would like to ask about the universal manufacturing. Is there any link? Does this universal manufacturing has any link with sustainable manufacturing? Does it have that scope too?
Oh, definitely. This is, in fact, you see, we have used some of the attributes to actually describe universal manufacturing, and that list is dynamic. And definitely sustainability is something that may really override a number of other attributes. But sustainability is going to apply to all type of manufacturing. It will be difficult for manufacturer to survive, especially I think with the new generation, which is more sensitive to environmental issues, not to be sustainable. So in a way, it's like resiliency is something that has shown up. It existed for a long time, but I don't think that we have taken really resiliency very seriously. So most of the time when we talk about resilient manufacturing or resiliency in manufacturing, we focus on how to deal with aftermath of disasters. But the idea is that we should design manufacturing systems in a way that they become resilient, so that when any adverse event happens, the impact is going to be minimal or ideally none. And the same applies to sustainability. We need to think ahead of time. And this goes back not just by just focusing on manufacturing only, it's not enough. We have to go back, look into products, how we product design, and then what we do with product afterwards. I think there has to be thought, maybe reusing products. So all these, methodologies, 10 R's or 12 R's that we have in sustainability, they need to be considered. And definitely, yes, universal manufacturing. In fact, it has more potential to address sustainability than maybe or any other forms of manufacturing models.
That's outstanding. And also it could even prevent crisis in that aspect, wouldn't it?
Oh, precisely, because, like what you see today, sometimes I'm not sure sometimes you may get email from a company, they're looking for something because, they don't have components or they are looking for manufacturing capabilities. I've received many emails where manufacturing company made me think that I'm entrepreneur or CEO or some company. And because they're looking for specific manufacturing capabilities. Well, this is 21st century. We shouldn't be using, phone or email to look for capabilities. We should be prepared for this. So we should be in cloud. So whenever any disruption happens, it's much easier to deal with, and you know, sometimes there was this need to rapidly increase manufacturing capacity, and again, single company couldn't do it, and we actually, you know, we don't know much about equivalency of manufacturing, which could be expressed in some similarity matrix. That, you know, I may not have the most efficient way to manufacture this sort of additional volume of products, but I have the capability to do it. So that's also important.
Thank you very much, Doctor.
Thank you very much, Adrieli, for the question. I see another hand raised by Wahad Al-Masri.
Hello, Professor. Thank you for your interesting talk. However, I would like to go back with you to your slide 14, because you were speaking about getting all the designs into the cloud, and the manufacturing is somewhere else. Well, somehow in my research work, we are trying to bridge this gap between the manufacturer and the designer, because, you know, we need to see what happens when the design is printed, or the final product, to see if we need to update the design. And don't you think in that way we'll be actually adding more gap to the gap that already exists? And additional to that, when we speak about cloud, there are a problem always of intellectual property of designs. Currently, you know, like the mechanical designers and the huge companies like Dassault, like AutoCAD, all of those kind of companies, they always don't share, let's say, like, because of intellectual property of designing. Cloud kind of comes not aligned with intellectual property. So what is your say about that?
Yeah. Okay. So let's start with your second question first. Yeah, yes. Right. So there's this issue of revealing. Really, companies afraid of revealing. So what happens? Sometimes this is just a myth, because just of not knowing, and you know, so I approach this from data perspective, because essentially whatever it's going to be present in the cloud is derived from data. So no one is going to basically display in the cloud specific data. So whatever it's everything will be processed, will be aggregated, and any company will have full control of what they share, with whom they share, at what stage. So this is something that we have learned. And I could, if I had more time, I could go into details how sometimes we work with some companies and we're able to basically, well, teach them that basically sharing this has no implication on revealing any know-how. And we know it's going to be. So obviously you also know that we have this sort of integrated model that almost whatever is shared at very, very high level. But in a typical manufacturing, what you know, the reality is there's only a few manufacturers of machine tools. So in essence, the knowledge is public. So if I'm telling someone, I can show in the cloud that I have two machines of two Okuma sort of milling machines. Well, that's you know, many other companies will have it too. So some of this is really benign sort of knowledge, but it's again more of education and sort of, you know, having really look at sort of, you know, model development, that, you know, rather than sharing just raw information, just basically putting them into some graph models or other suitable forms. You know, so that's maybe the second. Now the first one is that, yeah, obviously we have made progress. So because we in terms of design, we are designing basically just for itself, right, without considering manufacturing. Then we went for this design for the dedicated manufacturing. We have already devised some rules. So now the assumption is that there's already knowledge how to design for. So even if I'll be designing not for specific manufacturing basically capabilities. Well, but there will be many equivalent forms of manufacturing. So this knowledge design for manufacturing is very important, and it needs to be codified and become maybe more unified, because it exists in different pockets. And again, this universal manufacturing doesn't have to happen as sort of one solution. There might be different, you may call it, in today's language, consortia, that they decide to work among themselves and share information. And again, this can be justified. What happens in reality, that today you have two competing companies, tomorrow they say, well, we are merging. So I think so there's some kind of strategic decision that have to be made. But I see that the universal manufacturing is going to happen not maybe as one solution, one cloud-based, but rather sort of a number of those, and over time, again, like as merger and acquisition happens among corporations, the same merger and acquisition may happen again, among those basically universal subspaces.
Okay, cool. Thank you.
I see another question from Andreas. We have a couple of minutes more for just another question. Please, Andreas.
Thank you very much. Thank you for the talk. I have my question is on two aspects. The first is product quality is something that is a concern. I think I'm thinking when I do something the first time, I will probably make a lot of mistakes, and also in manufacturing, if you do something for the first time, you're probably not very good at it. If you kind of specialize and improve the quality over time, and this is the one aspect, and the related aspect is human worker experience is something that is also gathered over time. And in addition, I think it is difficult to share digitally. So my question is, these concerns, are they present in this universal manufacturing model? And if yes, how would these be accounted for?
I think so, yeah. So both the quality and human expertise, yes, definitely. Again, those also can be modeled, because and somehow reflected in those models that we present in the cloud. So it's, as you know, this, I don't think that such a transformation is going to happen overnight. Transformation to universal manufacturing. So it's going to take some time, and definitely, well, capacity, it's manufacturing capacity is probably the easiest to handle. But there's a lot of those basically intrinsic issues, including quality, reliability, and as well as human expertise that need to be reflected in the models. So it's also that we know it, that it's difficult. The goal is to design and manufacture and be right first time, but in many cases this is obviously not true. So there will be also we need to run some production experiments, and again, and this could be part also of this manufacturing universe that will have some experimental facilities where that maybe the initial run of new designs can be basically run and basically we that to check whether there's some issues, and then afterwards we could move to this more general space of universal manufacturing. So in essence, this universal manufacturing could mimic what one manufacturing facility. It's simply that there will be multiple copies of it, and maybe even more resourceful, because in one specific company, we might be not able, we cannot afford sometimes to buy a machine tool that has a maybe utilization of maybe 3%, while in this manufacturing cloud, we will have opportunity to actually to use such machine. So in essence, this may actually even speed up innovation, because sometimes manufacturing innovation is delayed, is stifled because of lack of specific manufacturing technology. This way, this very well, the technology that sort of maybe is the latest can be accessed by anyone. So I agree with you. Those are, I mean, this is big undertaking, and a lot of those soft issues have to be worked out, including, well, you know, that what we addressed in previous questions, the design for and you know, quality, and as well as just sometimes very some also specific operational issues. But again, there's also not going to be maybe one type of this glue, this manufacturing, this contractual arrangement that's going to be made, because it's you know, it's also possible that one manufacturing facility, one manufacturer may use another manufacturer with different degree of control. You know, in maybe one of those control modes, first manufacturer will have access also to workforce, to expertise of the other manufacturer, but maybe indirect. So there's this only upfront agreement that, well, I want quality assurance, I want reliability, but of the product, but you don't need to tell me how you have delivered it. So that's also part of the. So in essence, this is mimicking enterprise of today. Is just more distributed than we have seen thus far, and probably just more aspects that can be considered, because we assume that this is going to happen in digital space. So we'll have more opportunities to optimize in multiple really criteria.
Thank you very much. I don't know, Andreas, if you have one.
If you want to follow up or anything else, disagree with me, agree with me. That's, you know, I'm fine. I like challenges. So
if I may have the time.
Just
okay. So the follow-up question would be: do you think that maybe a standardization would need to improve, and also that maybe designs need to be more robust, because of you would probably expect more tolerances in the materials, and maybe also more simple, so that you kind of make use of this universal manufacturing system to a greater degree. Is that something that we should expect with this universal manufacturing?
I thought, well, thank you. So I thought about it, right? Definitely. Standardization, yes, it is, because, you know, we need to basically speed up communication, so we need to devise a different language. I view all standards almost as a language, you know, and this is happening. You know, if you look at the manufacturing floor, we have this empty connect standard. Well, that has become ISO standard. So in terms of sort of data exchange, under sort of data modeling has emerged. Then also, it's also, these changes maybe in design really philosophy. And again, this we are not going to cover 100% of products, but what you just pointed out, that we maybe use some simplified design, more standardization. Yes, it may happen, because you know what? Sustainability may get us there, for example. Because if someone comes with new organic material, and basically because we may run even out of some materials, or this would be this one, that material that is basically socially acceptable. So that everyone run out of it, and because by itself, that we may follow some standards, because this could be some new material that we didn't have that much experience. So better basically on a now basically safety side, let's be more conservative and design products in a specific way, and sort of so I think this really changing environment that we see around us will push manufacturing into one direction. I'll also say that if we knew exactly what the direction is going to be, that would be best. But at least what we have to do, we have to come with concepts that that will be available for discussion, and the future will show how ultimately what ultimate model will emerge. But we know that there will be changes, and more resources, more decisions will be based on data. And this is so the framework that I presented, I sort of abstract what I see, the changes, and made some assumptions, and that's the model that I see for the future.
Thank you. Sorry unfortunately, but we are running out of time, and we have to move to the second speech. So thank you once again, Professor Kusiak, for the...
Okay, thank you very much.
And this is just a certificate of appreciation that we will deliver to you by email. Unfortunately, we can't hand it to you in person, but we hope to meet each other very soon.
Okay, well, thank you very much. Yeah.
Thank you very much.
Great.
Thank you very much.
Yeah, bye.
And now I would like to introduce the second speaker, the second keynote speaker. It's Professor Tuğrul Özel. Professor Özel is full professor of Industrial and System Engineering and the director of the Manufacturing and Automation Research Laboratory at the Rutgers University in New Brunswick, New Jersey, in the United States. His research focuses on smart manufacturing, metal additive manufacturing, and 3D printing. And his research has been funded by several institutions, including the NSF, the NIST, the NASA, and so on, and the industry, of course. He published over 200 peer-reviewed articles, and he has a H index of 51. He's the editor-in-chief of the International Journal of Mechatronics and Manufacturing Systems, and editorial board member of several international journals. So his talk today will be about digital twin development for simulation of machining and metal additive manufacturing processes. So thank you, Tuğrul, for joining us today, and I'm pretty sure the audience is eager to listen to your speech.
Thank you, Antonio. Can you all see my presentation?
Yes.
Very good. Thank you for your invitation to give this keynote talk, and I'd like to start by looking at the hype cycle for the emerging technologies. And these are the technologies, innovations we keep hearing in the news magazines as well as in the research articles. So digital twin has been identified as one of the emerging technologies in 2019. And at the time, it was expected to be at the mainstream adoption within the next 5 to 10 years. And it was in the upcycle of this hype cycle innovation trigger. In 2020, other concepts came out as the innovation trigger stage, physics-informed AI, AI-driven innovation, digital humans, and at the time, 2020 survey, digital twin has already passed the peak of inflated expectation cycle, and it's trailed by smart factory, machine learning, autonomous things, and digital thread. So some of the things that we're going to talk about today are also in this hype cycle stage. And now it's expected that within the next 2 to 5 years, digital twin be in the mainstream adoption. Let's review a few definitions based on the level of integration between a physical object and a digital object. If the connection between the two is just the manual data flow, digital representation of an existing physical object, and most of the simulations, engineering simulations, fall into that group, they're just the digital models and no automated data exchange exists. In case there is a feedback or there is a one-way data flow from the physical object to the digital object, for example, some conditions change in the physical object that can be presented in the digital model, and this becomes a digital shadow. So, and there is some there is some changes in the physical system affects digital object. But the digital twin definition requires interaction in both ways between the physical object and the digital object, and with an automated data flow. That means that continuously both will feed each other with a rich set of data and information, and then with the hope that physical system will be improved and the digital system, digital model, digital twin will keep updating itself to that end. Other definitions offered for digital twin prototype where the virtual description of a prototype of a product and containing all the information required to create a physical twin exist. And digital twin instance is defined as a specific instance of a product, physical product, that remains linked to an individual product throughout that product's life. And then the combination of the digital twin instances form the digital twin aggregate, and there are various kinds of icons and things that are offered in industries and in the think tanks. And the digital twin environment is eventually a multiple domain physics application space for operating on digital twins. And as you remember seeing in the hype cycle, digital thread is also coming up. And what is the difference between digital twin and digital thread? Digital twin simply a representation of a product or a system, mimicking that company's machines, controls, workflows, and systems. Digital thread, however, is a record of a product or a system or system's lifetime from its creation to its removal, so more inclusive, and includes 3 stages of product innovation chain, enterprise value chain, and asset chain, and goes through all those chains, data chains, to form the digital thread. And this is up and coming. But coming back to digital twin and its relation to engineering simulations. So engineering simulations have been around for a while, and I will talk about that a little bit. And this is 1D, 2D, 3D simulation. And then the physical asset, it receives operational data from it, and then the model is calibrated. And then this is the development stage, physics-driven, and provides some information to increase the remaining useful life or predictive maintenance. And its operation of this physical asset in the shop floor or the manufacturing enterprise, it's data-driven. A survey is conducted by Altair among the small and medium enterprises, asking about what is the current level of engineering simulation adoption. And answers, 46% believe that a 3D CAD is happening, and multiple discipline simulations, 16%, and no in-house simulation, outsourced when required, 14%, and so on. When you come down to simulations, linked to the field data through digital twins, 5% believe that this is happening, adaptation. The primary machine segment surveyed among those SMEs, number one, 33% CNC machine tools, special purpose machines, followed by machine tools, and robotics and factory automation, and other machine segments. So according to the survey, the leading simulation benefit among all the simulation models was from manufacturing process simulations. 58% valued the benefits offered by the manufacturing process simulation, followed by 38% machine stress and vibration simulations, 31% thermal management simulations, 26% full system simulations, this would be discrete event type simulations, and 23% controls development. So this shows us the applicability of the engineering simulations, the process simulations for the product design cycle, and how it's adopted by the companies. And the digital twin adoption benefits were recognized as increasing business agility, number one, more first-time right products, especially in custom manufacturing industries, and better collaboration across engineering functions, and consistently applying product knowledge, and so on. Barriers, difficulties, challenges to the digital twin initiatives were also identified. These, number one, lack of personal resources, lack of necessary skills, experience in simulations, which is a significant barrier, and limited collaboration between the different organizations, costs for implementation, lack of necessary 3D product information, lack of correlation between test and simulations, and so on. So workforce, future workforce should focus on improving in industries fulfilling these roles that are presenting barriers to digital twin initiatives. And if we were to look at the engineering design and simulation relations in a historical point of view, we can see that the engineers discovered computers, and then computer-driven design took place between 1960 and 1984, and between 1985 and 1999, engineers started to use simulations to analyze their systems, and simulation analysis find a lot of applications. Most basic is the stress and thermal analysis. And between 2000 and 2014, we see that simulations are mostly used to derive the design. So simulation-driven design has become a common practice in this time frame. In the next cycle, between 2015 and 2021, it is becoming more of a reality that the digital tools, digital model coming from engineering simulation, has found its place in digital shadow, digital twin, and as I indicated, as a part of the digital thread to cover the entire life cycle of a product or a system. And let's now look at, within this context, our discussion or presentation title today, which is machining and additive manufacturing processes, a large group of processes among the manufacturing processes that take advantage of the digital twin in this context. Digital twin for machining systems should include digital twin for the machine tool, digital twin for the cutting tool, and digital twin for the workpiece. They include static, dynamic, and thermal behavior of the machine tool, cutting tool, the process, the chip removal process, as well as digital twin necessity for the workpiece. How can workpiece information can be digitized in order to feed into this system. The ultimate goal is to produce a smart and zero defect manufacturing. There are various kinds of solutions offered, or rather frameworks, that use AI-based technologies. So for example, AI-based detection and predictions. input data is collected, and then in the virtual environment, machining is performed. And also this results into training of deep learning, machine learning algorithms to be used to support actual physical system. And then the physical system is actually providing continuous data flow, data stream through sensor fusion in order to fulfill this interaction between the two systems. And potential benefits are the increased productivity, overall system through optimization, increased process reliability, increased product quality, and so on. In specifically how this can be achieved in a lower level, I would like to give you one example from our past studies where we use machine learning-based surface predictions in manufacturing processes, in particularly machining deformation process. Titanium machining as the physical object is the titanium workpiece material, and the digital model is the chip removal model, essentially machining model, where a finite element simulation is used, and it provides thermal and stress predictions as well as other results. And it is, in a sense, a digital shadow of the machining process. As a result, it provides input to the physical object, which is the machined workpiece material, which provides a feedback about the, for example, the grain sizes and the volume fractions after the machining, how the microstructure is affected by the machining process. To be able to capture all of this through some surrogate aggregate models, machine learning, random forest regression is offered in order to connect the relationship between the cutting tool and cutting conditions and the grain sizes and the microstructure and the microstructure hardness. To make this a realization, to obtain hardness versus temperature information is used, and then surface predictions for developing a digital twin for this machining process is offered as a digital result, predicting the depth below the surface hardness distribution with respect to time. So during the cutting process, one can actually see the changes in the hardness in the digital model and then adjust its properties or cutting conditions to optimize this. Another perspective in the framework is AI-based cutting force predictions. And in this case, classical methods, mechanistic force model, most force models are used in combination with experimental measurements. Typically, they need each other to survive. And on top of that, a machine learning, deep learning model is offered to use this data obtained from both mechanistic and also experimental model, and then improve the robustness and the reliability of the force predictions. AI-supported decision-making tool. Another example is the AI-based chatter detection. In this case, a lot of dynamic model for the machine tool and the machining process are offered, but by adding an AI-based layer to it, that provides a better predictive capabilities. And surfaces obtained with different kind of force signals for a stable cutting, transmissive cutting, and unstable cutting is converted into different kind of surface quality. And we know that there is a stability loop for the machining chatter, and these informations are used, and the cutting force signals are converted into so-called scalograms, where the images are used to train convolutional neural networks in different convolution layers, and then a fully connected layer is added in order to achieve a classification so that the surfaces are recognized as stable, transition, and chatter-produced surfaces, and the machine tool can then become more intelligent to avoid and in the dynamically changing cutting conditions to achieve stable cutting, and the part quality is assured. Another example in the tool design, chip formation. This is from one of our latest studies in order to investigate textured cutting tool surfaces. Three-dimensional chip flow is predicted, and where we have no chip extrusion and low and mild extrusion. And then this information is used to design a cutting tool. And also shaped cutting tools are also designed in order to avoid collision in thin-walled cutting of thin-walled work with structures. Digital twin for machining is also holistically reviewed, and then the current state is that the digital twin will require a lot of digital shadows for the workpiece data, process data, and so on. And the models for the digital twins will be developed. These are piecewise models. And then when they're integrated into a modeling framework, they will then complete the whole scheme of obtaining a digital twin for the entire machining system. The rewards are essentially application, the analyzing process, optimizing, and predictive quality control and documentation. For the additive manufacturing systems, digital twins are also offered and are currently under development, we can say. The benefits include reducing production cycle time, reducing number of defects, and increasing the quality of products. And the software companies are offering various kinds of simulation tools that address this. And these are typically geometry and also physics-based simulation models. They're able to forecast the temperature, velocity, cooling rates, and solidification rates, and etc. The AM simulation digital concept will actually provide a link between the physical process, that is the manufacturing process, and its digital twin that will require sensory data and then generate continuously improving digital models and then be used for decision making. And through the measured process data, physical process will actually provide input to the digital twin. In exchange, digital twin will provide model decision to improve the physical process. But these are very difficult tasks to achieve. Let me give you one example, digital twin concept. In order to obtain various kinds of predictive outputs from an additive manufacturing process. The particular process we're looking at is a laser powder bed fusion, and physics-based simulation models can be offered in the microscale, mel-pull, and mesoscale layer-wise, and part scale in 3D porosity, for example. And that the physical part manufacturing needs to be improved by providing simulation, validation, and data flow continuously. In return, process is monitored and in-situ and ex-situ measurements, providing a data flow feedback for the improvement of those models. And then various input-output relations can be obtained once those physics-based simulation models are established, and through the surrogate models, which are less expensive than the actual simulation models. Physics-based simulation models, let's review them, what they are currently. For example, those could be very basic two-dimensional thermal models where mel-pull size and shape can be predicted, as well as the time and temperature history of the process. And if you look at the literature, we can see various kinds of solutions are offered in that regard. Here are some simulations for thermal fields, and we can see as the 3D part is built, temperature history of the build. And this is offered for directed energy deposition, thermal field, layer to layer, as well as other additive manufacturing processes, mostly for metal additive manufacturing. And for the design, one of the important things is to know the displacement of the part that will be built, because the building process, the manufacturing process, will incur a lot of inaccuracies, including displacements. And these tools are available by various companies. For example, Materialize and Simifac Additive, you can see that the total displacement of the parts as well as the support can be seen. And after the support is removed, that the residual stresses, thermal stresses, will result in total displacement as an end result. And this is highly useful, beneficial for optimizing the geometry in connection with the topology optimization. Here we can see two examples offered for topology optimization, but these are not connected to the particular manufacturing process simulations. These are in the design stage. And for the displacement, we can also see that is highly important, especially for the thin wall structures, where they will be very sensitive to those changes. At a micro scale, various kinds of simulation models are offered. These are powder bed fusion or powder fusion simulations. You can see that uses various kinds of physical principles. So, for example, computational fluid dynamics or powder particle dynamics, and to be able to see the multi-scale physical events taking place during this process. In addition to that, other engineering simulation tools, for example, this simulation tool is showing a additively fabricated heat sink and how it actually allows the heat flow and dissipate the heat. All of these combinations of digital models are currently unlinked and in order to form digital shadows or digital twins. And for example, this is a computational fluid dynamics model, molten metal flow simulation. It's nicely showing, but it's irrelevant or it is not connected to thermal simulations, for example. But it actually shows the detailed events taking place, the heat conduction versus the heat convection. Heat convection is responsible for the phase changes in the liquid to the gas stage, heat convection. Heat conduction is from solid to liquid changes. Even those simulations require quite a lot of calibration in order to be robust and reliable. One other aspect is what kind of mechanical microstructure is obtained, and microstructure simulations use various kinds of methods: phase field method, kinetic Monte Carlo method, and cellular automata method. Here are two examples we see for cellular automata and phase field offered in the literature. We also conducted various kinds of thermal and solidification simulations based on the essentially heat conduction and heat convection equations solutions, numerical solutions, which are validated with thermal measurements, and then thermal fields are used in the phase field to predict the microstructure, solidification microstructure. And these are two simulations that are connected to each other. So thermal field provides a solution for the multiple boundaries, and that is inputted in the phase field in order to show that the essentially nucleation process and how within the multiple material crystallizes and forms a end result solidification microstructure. Can this be controlled by the system input to the machine tool, and also knowing the material property changes? Another example is how to develop a digital shadow by using in-situ monitoring and measurement of the multiple. And these are images obtained with a high frame rate camera and thermal camera, and then they're converted by using machine learning to a digital shadow of the multiple. And now this can be analyzed in a virtual platform in order to see the effect of changing laser powder bed fusion parameters and its effect on the powder material spatter, multiple formation, and dynamic multiple behavior. Another example for the digital thread in how we can actually look in the product's life cycle is doing some X2 analysis on the additively fabricated metal parts and looking at their surface texture and using machine learning in order to capture the relations between the surface texture parameters and the laser powder bed fusion parameters. Then this information can be used for a life cycle model to improve the life cycle behavior of the additively fabricated parts. As you can see that there are various kinds of models offered for AM simulations, but there are a number of shortcomings. First of all, thermomechanical AM simulations are available, and to determine the residual stresses, distortions, and the temperature history, but these simulations are very complex and they take very long period of time to develop and also implement, as you can see from the SME survey. And also there are lots of assumptions make the simulation predictions with some errors. And those errors can actually lead to some incorrect decision making. So this complexity can be overcome by offering some other approaches. For example, we're going to see some machine learning approaches in order to provide some piecewise models here to detect the defects in the process. Convolutional neural networks are used to identify the defects from the images taken in the layer-wise information. And again, the same method is used in order to identify defects, this time from heat maps images. These are readily available most of the additive manufacturing machines, where they actually take various kinds of layer-wise images, whether some optical images or thermal images. And then there are other approaches offered, for example, how to provide a quality assurance and quality control by using some systematic approaches, as well as graph theory approaches to quickly calculate roughly the temperature distribution within the part without using lengthy thermomechanical process simulations. And eventually, the big idea is to control and optimize the manufacturing process, and then use the sensor data and use machine learning in order to create decision agents to help improve this control process. One other interesting cycle is that this physics-based modeling and simulation, as well as process monitoring, provides insight to the manufacturing process, and quantification and variability of the modeling can be captured by continuous rendering of this cycle. And then the end result is to improve the microstructure and material characterization for mechanical properties that are desirable for the end product and that are robust and reliable. And to this end, there is a strong need for surrogate models. Surrogate models are models that do not really need this multi-physics simulation results, and can be actually offered as a tool in order to provide a quick solution. Okay, so, and surrogate models can actually be really useful in order to provide, as I mentioned to you, quick input-output behaviors, but then actually they can use the physics-based AM simulation models, and their behavior is captured by the surrogate model. And just to give an example, the expensive route would be the design parameters are used to obtain the simulations, and the outputs are offered. The surrogate model is a cheap way of providing a solution, but actually surrogate model continues to learn from the simulations. And that, in that case, not always a simulation needs to be conducted to obtain the outputs. And to that end, machine learning models actually provide a lot of possibilities to connect the input parameters and material properties to the desired outputs. For example, multiple geometry, multiple classification, and the machine learning can actually provide this possibility, include rich set of machine learning models, regression trees, random forest, support vector machines, neural networks, and Gaussian processes, etc. The envisioned anatomy of a digital twin includes that there are certain things already developed, and there are certain things that are already developing. For example, we know the thermal fields. We can actually have certain conditions that avoid defects, geometry and structure, and more confidently we can identify that. However, microstructure and mechanical properties, residual stresses, and other compositional changes, grain size and texture effects, more refined predictions are not as developed. The idea is to produce robust printability that has the ability to resist distortion, lack of fusion, balling, keyhole effects, and alloy composition change. And to that end, impact of machine learning and AI is already happening. We see that machine learning is used for various kinds of tools, as I explained, process surface relations, for example, and process monitoring and machine learning is providing digital shadows to be developed. And then process control by defect detection is already part of this machine learning and AI applications. For the future outlook, continuous improvement of the physics-based simulations and their integration with the machine learning should be done. And these should be integrated into digital twin. And again, we have black box approaches and white box approaches where we have physics-based simulations, but they need to merge in a gray box approach, as pointed out by Aachen University, in order to actually create digital twin that is taking information from physical models, data-driven models as well, bear on a common strong digital twin that allows engineers to design products better and also manufacture those products better. Also, human-machine tool collaboration with AI also needs to take place, that quickly operators can see this digital information in order to do various kinds of tasks, including monitoring the manufacturing operation, providing the maintenance, and quality and reliability issues. In conclusions, simulation models are out there and they help accelerate development of digital twin in automated machining, additive manufacturing industries. Machine learning and additive artificial intelligence are used in machining and also additive manufacturing processes to capture meaningful patterns in the presence of large amount of data being collected from these manufacturing machines and systems. And computational modeling and digital twins are becoming increasingly important. Simple physics-based simulation models for the process provide insight on the physics of the process, but it's not sufficient. They need to be supplemented with physically informed machine learning, and the interactions between the physics-based models and the data analytics should be strengthened in order to develop predictive and useful digital twins in the era of Industry 4.0. And the sensors and hardware are in the core of this capability, because the sensors and the new hardware will provide both data collection and sensor fusion, and in return, sufficient and meaningful actions in order to correct the situation, in order to adaptively improve the manufacturing enterprise. and also some unique experiences developing these data-driven simulations and surrogate models are available in literature, and I have presented some of them to you. And from the physical process or the machine, and then this would be feedback into this process design and automation system. There are some opportunities and challenges remaining, and those are always good things for us researchers in order to make this improvement happen. So thank you very much for listening my presentation today, and I'm happy to take if you have any questions.
Thank you very much, Michael. And I would like to invite the audience to make questions. Feel free to raise your hand. So I see the first question from Florian. Florian, please.
Yes, hello. Thank you for a very interesting talk. You made some indications about being able to use surrogate models to work in parallel to simulations and learn from simulations. And I would like to hear if you have any remarks on the current perspective of how much, so to speak, the model, the machine learning part of the surrogate is, so to speak, modeling the unknown, and how much, so to speak, the surrogate itself is something like a differential equation or a conventional way to approach the physics, for example. So basically my question is, do typically AI models include the performance of the underlying conventional model, or are they typically used to as add-on models to correct the simple model or the conventional model in the sense of correct the residual error?
Very good question. I think the need for the surrogate models are coming from, the physics-based simulation models are offered, and they have been around for a long time. And in the context of Industry 4.0, these piecewise models need to be put in a perspective, and then they need to be connected to the digital information, digital data of the physical object. And in that case, we know that these, in case of machining, you're actually simulating a very short distance, and you're getting a lot of information about the physical variables, but that's not really production output. And surrogate models are fulfilling this role, making links, connections of these individual simulation model, physics-based simulation models, to the digital twin within the context of digital thread. And in return, they will automatically obtain their input parameters from the physical object measured by the sensors. For example, you define a velocity in your machine, and you believe that this velocity is achieved during the process. You're not so sure, you never measure it. And then if there are sufficient sensors to provide this feedback to your physics-based model, and a physics-based model through sensitivity analysis surrogate models can quickly, the surrogate models can quickly provide the adjustment needed for the machine tool.
Yes.
And so the surrogate models can provide the quick acting back to the physical system. Physics-based simulation model, classical simulation models cannot do that. And Other question you ask, whether they're mathematical equations, differential equations, they could be anything. They could be anything. But the thing is, machine learning based models that are data driven can really quickly prepare and present a surrogate model. You know, most basic surrogate model you can think is a linear regression model.
Yes.
And in that case, you just replace the simulation, you just replace the experiment, you use a linear regression. But today, thanks to the mathematical computational algorithms and the computational power, and also embedded systems, right? You don't have to take this to a computer. You can have an embedded system within the manufacturing system that quickly can calculate those surrogate models and feed back to the machine tool. But where the surrogate models learn the behavior of, let's say, process, cutting tool, machine tool, additive manufacturing machine, laser behavior, is through those pieces of surrogate models.
Yes, thank you.
Thank you.
Thank you. Is there any other question? Yes, Jan.
Yes. Hello. Thanks for the talk, for the very interesting talk. So I'm curious. You mentioned something like the machine learning techniques you're using are from the white box part as well as from the black box part, and what would be most optimal would be some kind of gray box. I was curious why. What is the reason for this gray box to take best of both worlds, or what exactly do you mean by that? Because actually we are working on in our research group is taking white box models and infuse them with domain knowledge from the physical domain. So we don't need those black box model. We are trying at least to don't need those black box models as they are not interpretable by nature. So I'm curious how you would combine those two models from those two worlds to get the best of both.
Very good question. I think that slide, it didn't actually go into so much in detail. Current approach is black box approach. It was offered, for example, neural networks have been around for a long time, oftentimes is seen as a black box. Now, there are certain things that is very difficult to simulate and predict. And in that case, just experimental based data is used to capture that behavior. So if that black box, let's say it's a surrogate model, and then starts learning from the physics-based, white box models, which like deterministic models, they give flat out results, and then improve itself continuously, becomes it's a hybrid model. So in that case, they kind of merge in what we call the gray box model. The gray box model name is tokened by the Aachen researchers, just to kind of give you the idea that the physics-based results are valuable, but they're not sufficient. You still need some kind of black box solution, black box model. But then black box model can learn from this, the rich set of white box models available. And what you're doing, as you mentioned, from what I understand, and also I watched your presentation and paper, you're kind of doing the same thing. You're kind of actually creating a hybrid solution that your model learns from the physics of the process, and then, but then actually becomes a virtual sensor, virtual tool, right? As part of merging the two base. And the role of the machine learning is to expedite this process, provide quick solutions, powerful quick solutions based on the statistical learning, and other mathematical algorithms to actually provide strong, robust, and continuous learning capabilities in that gray box in the middle. We call it physics-based, data-driven. So both words merge in that regard.
So everything what is not explainable by using just the physics, just formulas you are presented to, so you have already there. You try to estimate with a data-driven approach. So you're doing a understand. Okay.
Also, any kind of variability in your physics-based models, you're predicting, but then you need a sensitivity analysis. If the conditions change 5% plus minus, how would your model behave? That can also be fulfilled by this machine learning models.
Thank you very much, Jan, for the question, and Professor Özel for the answer. So I would like now to go towards the end of this keynote talks, and let me thank you once again, Professor Özel, for your speech, and of course, also in your case, we are going to deliver by email the certificate of appreciation for this interesting talk. And let me thank both you and again Professor Kusiak for joining us, and hopefully next year we can meet in person.
Thank you very much, Antonio.
Thank you once again. And now I would like to invite Professor Longo and Professor Affenzelle for the Best Paper Award ceremony.
Thank you, Antonio, and thanks to the two keynote speakers. Their presentation was actually, they were very, very interesting, providing this nice overview from a universal approach toward the specific problem in how to model a digital twin in machining. So I really appreciated the two presentations. And actually, we were able to see, I feel, along the last 2 days, a number of very interesting presentations and sessions and very high quality research articles and presentation. And I was able even to see that there were students connected to the session and to the presentation. And I feel that this is an advantage of going online, because I see some master students connected from different universities. It means that, okay, we are not face to face in this moment, but at least some students that perhaps they were not able to travel and to attend the conference, they can join this 3 days presentation. And it is even nice to see that there are a lot of people connected right now, even if there are problems due to the different time zones, and so sometimes it's difficult to join the session on time because we are connecting from different countries in the world. So it is a very interesting community that is growing up around this international conference, and therefore we take again this opportunity, let me say, to thank you all of you for participating, and obviously we wait for all of you next year to be physically in Austria. And as usual, we invite all of you to even to take an active role in the organization of the conference. If we are able to create more sessions and more tracks, we can create more synergies and more opportunities to for collaboration. During one of the sessions today, I was mentioning that in the first edition of this conference, we sit down around the table and we propose to do a research proposal at European level, and now that project was funded, and we are working with the partners on that project. And the idea started around the table during this conference. So it is, I feel, a huge opportunities that we may have if we create more collaboration and more synergies. In addition to the scientific presentation that are important, I feel that doing networking is even more important, as well as it's important to award in some way best papers and people that are providing excellence in our sector. And that's the reasons of this, let's say, ceremony, that it is also a tradition of this conference to award different type of best papers, as well as persons that have provided help in the reviewing process. We do so. welcome to this Best Papers award ceremony. Next slide, Antonio. I feel we can just recap which are the best paper that we are going to give. We will have a scientific best paper award, as well as this is the classical, let me say, best paper award that we usually give at the international conference, but we do also have an industrial impact award. So we are going to award the paper that has, in some way, according to the ISM organization committee, has provided a very good industrial impact. And there is also an additional award that is related to the best service innovation paper that will provide in collaboration with the ICIP Association. And finally, we are also going to award the best reviewer, because it's important to mention that the success of this conference is due to the International Program Committee, and it is due to the work that these people are doing in not only in inviting papers, but also in reviewing paper, in selecting paper, and supporting the final publication. So they for sure deserve the best part of people of this team. They for sure deserve an award as well. There is also with me Michael Affenzelle, the other general co-chair of this conference, as well as Antonio, that was chairing the previous session. I don't know even if Wei Ming is here, the other program co-chair, but in China it's pretty late, I suppose, so perhaps he's not joining. No problem. So Michael, I don't know if you don't want to say some words before going to the awards.
Okay, thank you very much, Francesco. Well, I would like to state the reminder that usually we should be sitting in the Böstlingberg Schloss with a nice overview over Linz, which we will hopefully do in about 1 year. And as Francesco said at the opening, we should prepare some drinks for the best paper ceremony. I did so. I have an Aperol Spritz here with me, which you get all over Austria, even though it is Italian origin and therefore very well suited, I think, for this venue, which has a strong background in the Italia-Austrian connection, but also with many contributions from other countries, especially Germany. I think from the contributions, it was Germany, Austria, and Italy, which made the majority of contributions. And during this virtual conference dinner, let's say it in that way, as a tradition, we honor the best papers, and we have three candidates among quite a lot of very high level papers. So according to the reviewers' comments, we had quite a lot of highly ranked papers by all reviewers, but we somehow had to take a decision, and we had a two-stage process in decision making for the certain categories of best paper awards. And Francesco, I don't know, should we state also the intermediate results of the three candidates, or just?
Oh wow, that's a nice question. When you are among the first three, you always believe that you are the one taking the award. So I don't know. It's up to you. Go ahead as you like. Let's see the next slide, Antonio, so we discover if.
So next slide shows the winner. So
we have only the winner. So I feel that we can announce the winner of the scientific best paper.
Let's announce the winner outright, in order to avoid the other two to be disappointed. But it was pretty close, I have to say. But let's go directly to the winner of the ISM 2021 Best Paper Award. The paper is entitled "A Cloud-Based Digital Twin for Monitoring of an Adaptive Clamping Mechanism Used for High-Performance Composite machining. It's from a Belgium group, and I hope one of the authors will be with us. Sam Wex, Stephen Robbins, Jonathan Bake.
Maybe Antonio, you can put the slide.
Yeah.
Do you see the slide?
Yeah, we have it.
So I see also Sam connected.
Yes, I'm present.
Okay.
So congratulations.
Yes, thank you very much for the appreciation. I've seen a lot of good papers with presentations this week, these 2 days. So I'm very flattered with this award. I will tell it to my colleagues who helped me with this award. Thank you very much.
Congrats, Sam. Really great contribution.
Congratulations. Congratulations. Now let's move to the maybe, okay, it could be nice if we can take a picture of as we usually do during the real conference. So if you can switch again on your camera, we can take a screenshot. He's gone. Okay, we took the screenshot. Okay, it's coming.
Yep, sorry.
Okay. Let's take the screenshot. Wait a second.
So smile.
Here we go. And now let's move to the next award, the Industrial Impact Award. Also in this case, as Michael Affenzelle was mentioning before, there were some very good papers. So obviously the decision was not so simple, and the organization committee was discussing to to give the award. But in the end, the award for the industrial impact goes to the following paper. Trainman, Magos, capture of dexterous assembly manufacturing know-how as new efficient approach to support robotic automation. The authors are Angel Dacal Nieto, Greg Agripoulos, Teresa Mendes, Julian de Calle, Ruben Paz Chibeira, Vasilo Postolos Souranis, Carmen Fernandez Gonzalez. So if you are here, please switch on your camera.
I do not see actually any one of the authors connected.
Yeah, it's a pity. Okay, in any case, we will send by email the certificate. There are no one, and I suppose they deserve an applause in any case. We can just good. And I would like now to leave the floor to Antonio for giving the ISIP award.
Yeah, I don't know if anyone from ISAP is also connected. If so, please feel free to switch on your camera and your microphone. Well, basically, this award is assigned by the ISAP committee. ISAP is the International Society of Service Innovation Professionals, and as Professor Kusiak said during his talk, manufacturing as a service will be the paradigm of the future. So the topic of service innovation is extremely interconnected with manufacturing and with Industry 4.0. So the best service innovation paper award goes to Digital Transformation in Metrology, Building a Metrological Service Ecosystem. The authors are Alexander Oppermann, Samuel Eichelberg, John Exner, Thomas Bock, Matthias Bernien, Rolf Nieprasch, Wiebke Ehren, Oksana Baer, and Clifford Brown. They are from Germany. So congratulations. I don't know if anyone is connected. And I just would like to say that the winners will be also acknowledged on the ISAP website and will be also awarded with a dedicated knowledge sharing badge in recognition of their excellence in service innovation. So are the authors connected?
Seems no.
Of course, we will deliver all the information by email to the authors, including the certificate.
Great. So now let's move to the to award the reviewers. As I mentioned before, their strong contribution it's in some way crucial and important for the success of the conference. And our community is really pretty active from this point of view, and therefore that's the reasons we are able to select very good high quality papers. And for these reasons we have decided actually to award 3 best reviewers, because there were 3 people that were contributing so much to the review process. And so the best reviewers awards goes to the following persons: Andriy Karitonov from Otto von Guericke University, Magdeburg, Germany; Grigory Piskulov, the University of Manchester, United Kingdom; and Patrick Barges, University of Applied Science in the Netherlands. So if you are here, you can obviously switch on your camera. Seems that we are pretty unlucky this evening.
Yeah, I do not see them.
Okay. They will receive a surprise being nominated during the award ceremony. Perhaps they will see the video on the YouTube channel. So we are done with the award also this year, but I feel this is also an opportunity, you know, to drink something together. So I would like to invite everyone to switch on the camera. So we'll stay a bit all together, face to face. It's virtually face to face. So let's switch on your camera, everyone, and you can take your. Good to see people. You can take something to drink. And so we can cheers together. Here we go. Okay, switch on your camera and come on, don't be shy. I can see just few people with the camera on. Maybe people, they are at home, they don't want to, you know, to switch on the camera. In any case, so cheers everyone, and thanks for joining this conference.
Cheers.
You can even switch on the microphone so we can cheers, we can hear each other.
Ciao everyone, I need to say bye-bye. Well, congrats for the winners.
Oh, you are walking.
Yes, I'm in
going
the
around
station.
somewhere.
I need to go home, otherwise there will be no train. Goodbye.
Yeah. Thank you for switching on the camera. And that's nice in the you know, in the online conferences you can do. There are people maybe driving at this time, coming back home, going around, but in some way they are with us, listening to the session. So this is really interesting. Great, very good. So again, thank you. I don't know, Antonio, if you want to add something before closing.
No, I guess we said everything. Nothing more. Just to thank once again everybody for attending, and of course we meet once again tomorrow morning.
Yeah, sure. Don't forget tomorrow morning again at 9 we start all the sessions. So don't be on late and don't drink too much this evening. Okay. Unfortunately and unluckily, we are not, delighting the typical Austrian dinner. I was looking forward for this, Michael, but we can't. We will try to do next time for sure. Great. Again, cheers everyone, and let's see each other tomorrow.
See you tomorrow. Bye-bye.
See you tomorrow. Bye.
Bye.
Thank you. Bye-bye.
See you tomorrow. Cheers.
Bye.
Ciao,
Bye.
Antonella.
Cheers.